All right, this is part 3 of Chapter 8. In this video, we'll finish up Chapter 8 by discussing categorical tests like the chi-square test, and then some some other additional issues about sort of simple statistical testing, including what do you do if you have different sample sizes and how to handle skewed distributions, and also how to compute effect sizes for the t-test. All right, so far we've looked at a bunch of tests for correlation and for differences between groups. What happens when you have categorical variables? And here's a data set that's built into R called hair eye color, and it looks at both gender, hair color, and eye color. And you might wonder whether hair color depends on eye color, meaning do people with, say, blonde hair, are they more likely to have blue eyes? This is something we think is probably true, because of the way genetics works, and people and the genes have in more northern climates have mutated or selected for light color because it's better at picking up, I guess, picking up vitamin D from the sun or something like that. So you might wonder if these are the same. And so first, you might think, well, why can't I just do a correlation here? I've got different values in two different sets. Why can't I just do a correlation? And then you'll think, well, what am I going to correlate? Can I correlate hair color versus eye color? Not really. Correlation requires you to have continuous valued variables. Even though there's numbers here, I guess I could correlate hair, eye, color, comma, 1, 1 to hair, eye, color, 1, 2. I've got to spell this right. And it even gives me an answer, but it's not even clear what that answer means if you start to think about it. And you might think, oh, why can't I do a t-test? Let me count the number of people who have brown hair for brown eyes versus the number of people who have brown hair for blue eyes. And that certainly would be possible, but I can only do one category at a time. And what if the hair equals brown didn't change, but other hair colors did? So what we'd like to do is look at a statistical test that can test for independence, and which means for a table like this, do we have the same distribution in each column? Now here I've got counts, so the distribution, I might have absolute numbers that differ, but I'd like to also then know whether the relative proportion in each column differ. So here you can see for brown hair, or for brown eyes, very few in the male, for the male gender, there's very few blonde hair. But for blue eyes, there's relatively many. So it goes from brown hair is about equally likely for brown and blue eyes, but blonde hair is 10 times more likely for blue eyes. So I'd like a test that would be able to figure that out. It looks actually for women even stronger. So here we've got twice as many women have blue eyes and blonde hair. I'm sorry, blue eyes and blonde hair than blue eyes and brown hair. And so this is maybe kind of strange. So maybe that means either, what are they asking? Are they asking what's the hair and eye color you were born with, or what's the hair and eye color you have in a picture? I'm not sure. So this just might indicate that either hair color is dependent on gender genetically, or through things like dyeing your hair. Well, can we know that for sure? Maybe this does just happen by chance. If these were the same, would we expect to see a distribution like this? In this case, I think it's probably, my intuition is probably pretty unlikely. But but who knows? And if I had a lot fewer observations, if I didn't have maybe 100 um, or more observations for every eye color, for every gender, and for every hair color, maybe you could get a pattern like this just by chance. So we could visualize this using a stacked bar plot. Here's men and here's women, and you can see, let me hopefully zoom out, we can see that for, I guess here's the big difference between hair color between men and women. Blue-eyed, blonde hair is much larger here than here. I could maybe make this a little easier by color coding the eye color, and now we have hair color at the bottom, and again we see this larger proportion under of blonde hair, blue eyes for women than men. Um, this is what it looks like if we just collapse across men and women. So I'm just adding the men column to the women column and getting just the hair color and eye color contingencies. And so we'll call that HC2, ignoring gender. Okay, so this is what I actually see if I look just at blonde hair. I see 7, 94, 10, and 17. Or if I want to look at blonde and brown hair, I can pull out just a subset. So I'm going to all right, so if we consider just the distinction between brown and blonde hair and eye color, maybe we can find a difference here, and we can see overall in this distribution there's a lot more brown here than here, so maybe that is a relationship that we would expect these two categorical variables to be related to one another. Well, we could ask, what's the expected proportion of eye color if we ignore hair color? So if we look at the expected proportion of eye color, we can see 30% brown, 40% blue, 15% hazel, and 10 or 11% green, which I guess probably is pretty, may match your intuition. Probably this is, I don't know what the population this is coming from, but it's probably pretty, it's not, certainly not Asian. It's, we've got relatively many blue-eyed observations. Let's just hair, eye, color. Let's look at where this actually comes from. 592 statistics students in 1974, and at some university in the United States. Okay, so this is the expected proportion, and I can multiply that back out and say, well, that's the expected proportion. I know that in my brown, blonde, I've got a certain number of brown hair and a certain number of blonde hair, so I can multiply that back out to form what the expected number in each of these should be. So if the brown hair was equally proportionate to the marginal means, which is the average here, and if blonde and brown were equal, you'd expect 87 and 38, and you'd expect 123 and 54. So here's the expected number, here's the actual number. So a simple test would ask, could this have arisen from this? Let's plot these against one another. That's the expected distribution. You can see that even though there's fewer blonde hair, the the distribution of eye color for these two hair colors is identical. So to find out if they're the same, I could take these numbers, subtract these numbers, square the difference, and then divide by these numbers. So if I look at this and then add them all up, and I get this number. So they're all going to be positive differences. And then that comes up with a statistic. And and so we could do a thought experiment and say, well, if there were really no difference, what's the expected value of this statistic? It's going to depend on how many are coming from each of the groups, and so it'd be larger if you have more values, and you might expect that the larger distribution, the larger numbers of groups here, you'd expect more distributions and things like that. So this statistic we just calculated is called the chi-squared statistic, and it has a null distribution. It has a distribution under the null given the size of this this matrix. And so it has a test against the null hypothesis. And if we do this, we can see if we do chi-squared test of brown blonde, that this matrix, it will give us a chi-squared value. The degrees of freedom is 3 because 3 is going to be the rows minus 1 times the columns minus 1. So it's going to be 4 minus 1, which is 3, times 2 minus 1, which is 1. The whole thing is 3. And maybe your intuition was correct that this is very unlikely to have happened by chance. These are really big deviations from having an equal distribution, and so this was very unlikely to happen by chance. So this would be a statistically significant difference. It was unlikely to have risen under the null hypothesis. Okay, so there's several ways you can use this chi-squared test. One is just to test against, let's see. One is just to test against a given set of p-values. And so if I look at HC2 and I look at brown, I could say, oh, I have a really good understanding of the distribution of blonde, but I don't know anything against brown. And so I can take this as a given and test this against this. Now this is going to be a little different because I'm not taking my assumption that it's going to be, these are going to be the same. I'm going to say this is the truth and I want to see if this is different from it. And so this test is going to be different. The chi-squared value is a lot larger, p-value is a lot smaller. And so if I did, here's the other version of it. Instead of saying I'm going to force P to be this, I'm going to, if you use them both, you get a slightly different test. Now the chi-squared test, sometimes people call it a non-parametric test because there's no assumptions of normality or skewness already, and it's used an awful lot in applied context where you just have categorical variables and you want to see if there's a relationship. So there is a Bayesian version though, and the Bayesian, you have some additional arguments you have to give it, and I won't go into details of that, but you can look at those in the Bayes factor library help. So this gives us the equivalent of the same test for brown versus blonde. And again, this is a very large number, so it's overwhelming evidence in favor of non-independence. And he says non-independence A equals 1 is equal to that. So another thing you might do, which is a little different, is you can test against equality. So I might guess, this is more of like testing for a fair die. You might think, well, there's 4 different hair colors, they should be equally likely. Can I test whether hair colors really are equally likely? And so it looks here like they're not, because this is about 4 times this. This should match your intuition that there's many more brown-haired people than red-haired people. And so we can fix P to be equal like this. And here the test is going to have a chi-squared value of this, and it's going to be significant. So there's evidence that hair color is not equally likely across different groups. This is just what we did above. Now there's other ways of running the chi-squared test. So instead of building the table, let me do this again. Now I've just sampled values that are independent. These are really independent of each other, and I've got 1,000 different letters, grades. Maybe these are 2 different tests, and I've got 1,000 people that I've looked at their scores on 2 different tests, and are they an A through an F, or I guess in this case, then I could use an ordinal scale, but A through F would indicate their choice 2 different times on a categorical scale. And then here's a third question I might ask. That's just yes, no, or maybe, which is on a completely different scale. So I could test chi-squared test of sample 1 versus sample 2. And here the p-value is 0.46. This is not significant. This is very likely to have happened just by chance, which is good because when I created these, they weren't created to be equally likely. Or I could do 1 versus 3. And here again, the p-value is very large. This is very likely to have happened just by chance, which is good because they were created independently. Now this first one, you notice before I gave it the table, for the hair color, I gave it the equivalent of this, which was the whole contingency table of A versus B that I can create with the table command. Well, this test, if I'd give it these 2 independent outcome values, is going to be the same. So notice chi-squared is 24.987. Here it's 24.987. So really when you run the chi-squared test this way, underlying it is building this table and doing the chi-squared test on the table. But I think for the Bayes factor, you have to build that table by hand. I don't think it will take these different arguments. Here's another table that specifies, this is sort of like the hair eye color, but notice we've got different outcomes. This is yes or no, and this is a bunch of categorical values. There's 2 different ways I could frame this problem, though. First, I could ask, are these independent? So giving a chi-square test, the table tests whether they're independent. That means, is this distribution differ from this distribution? And so here we see that they are not different. And if you look at, let's see how I did this, they're created so they're not independent. Of course, we could do a Bayes factor test of that same thing, and you can see again strong evidence for non-independence. But by doing the test this way, what I'm really asking is, in this table versus table of sample 1 versus sample 2. Okay, here it's the same data that's created in 2 different ways. This is looking at whether values for all the different pairings, whether values of one depend on values of the other. This is asking whether these two distributions are the same, sort of the marginals. So what it's doing is adding up the margins here and the margins here. And you can see by the way I made the table, for sample 1, F seems to be underrepresented, but for sample 2, F seems to be equally represented. You can see there's only 43 here. So you have to think about what is it you're really trying to test in a chi-squared test. Are you really trying to figure out if the overall distributions are the same? So this might be on a multiple choice test. Is F all of the above, and on one item people are not saying all the above very often and the other item they are? Or is it that the knowledge that they're saying, if they give E, are they more likely to give A on the other item? And so these are two different questions, and here we have independence of the contingencies, and here we have non-independence of the marginal distributions. So just be aware that both of these are reasonable questions to ask in different contexts, and you have to do you have to build these tables differently if you want to test this versus this. This is probably the most common thing to do, but sometimes people want to ask this question and they do this instead, and they're not necessarily the same answers. Okay, so that's that's it for the chi-squared test. Now we have some additional things about the t-test that we'll go back to. One is about normal and skewed data, and there's discussion in the book about trying to transform this, or maybe using alternate tests that actually explicitly model the distribution of something other than normal. This is probably most important for maximum likelihood or Bayesian approaches, which are explicitly making assumptions about the normality of the data. So what happens when you have different sample sizes? Here's two distributions, and they are related, and one has a mean slightly larger. And if I do a t-test of these, I can see that, oh, that's not significant, even though they were sort of generated to have an effect size of maybe larger than 1, but because of the small sample size, we didn't find significance. What if I were able to collect more data, but only in one of the groups? That's actually completely possible to do. It gives me a better, more precise estimate of one, but not the other. If I had the choice, I would like to collect data in both groups, but maybe you can't do that and you only have the opportunity to collect more data in one group. This can, so you wouldn't want to throw out trials just to make them even, and the t-test is robust to having differences in sample sizes. And so in this case, adding, so let's see. In this case, adding more to the one set didn't make a difference, but sometimes it would. And sometimes it would make it stronger, and sometimes if you don't have an effect, collecting more data in the other one will make you more convinced that there is an effect. But the t-test itself, if it's not paired, it allows you to have different sample sizes. I guess we've looked at that already. What about the differences between and within tests? So here's 3 random sets of data, and I'll call y1 and ya sort of linked to x1 and xa. And if I do, for the smaller data set with just 20, if I do a paired t-test, you see that this is not significant. And if I do an unpaired t-test, it's even less significant. So I'm less likely to find the effect, even though that it was true. And that should match your intuition that if these are linked, if I treat them as paired, I should get more power out of my test. But here's one where I have more data, and now it does matter. In this case, if I do a paired test, it ends up having a statistically significant effect. In this case, it doesn't. And so there's certainly circumstances where doing the pairing will have an effect as long as your pairs, there are systematic variability that can be attributed to those pairings that you're essentially able to factor out. If the two observations from each person are independent, this won't have this will make a difference. And what about if you have different variability? So here is y, and it's an x that's related to the x with different levels of variability. And you can see that in this case, it can matter. These are not identical, but when I have low variability, I have the same variability in x, but different variability in y, and I use a paired test. The low variability y is much more significant, statistically significant than this one, which doesn't meet even a 0.1 criteria of significance. So it is certainly possible, even in a paired test, to have different levels of variability. That just gets factored in. But you'd prefer to have low variability in all your measures. Okay, the final piece of this is to talk about effect sizes. And in general, journals like you to report effect sizes, and they're really good for sort of interpreting whether the effect has any meaning, not just whether it's statistically significant. Meaning is tough, though. You could have an effect size and still not be able to interpret it, but it gives you if there's any practical significance or what the practical level of significance is. And to do this, you look at the mean difference and subtract by a measure of the pooled standard deviation. So here are two ways of doing that for our y1 and y2 values. And you can see that, oh, practically, when I had all that variability, my effect size goes way down. So this really says how many standard deviations apart are the mean. And here it's 3 apart. And here it's 0.52 apart. And in some contexts, 0.52 may still be very large. In this case, it wasn't significant. It's still relatively large in some contexts, and you could have big effects in education if you had an effect size of 0.5. For paired samples, it's even easier. You just compute all of the differences, and you can do mean of delta 1 over standard deviation of delta 1. And here, so the effect size is negative 0.41. And then mean of delta 2 over standard deviation of delta 2. Again, the effect size is relatively small. What if, generally in most fields, an effect size of larger than 1 is something to really take note of. So these would be large effect sizes in any field. Maybe in some areas like visual perception, you'd expect even larger than this. But even effect sizes down to 0.3 and 0.2 can be important. If you are selling something in a business, effect sizes even that small might mean that you still can increase revenue by 20% for a certain sector, and so you could still make millions of dollars off a effect size this small. It just depends on both how precise and reliable your measurements are, so how much noise you have in there, and the difference between groups. So you should always compute this when reporting a t-test, and in any statistical test you should report effect size and look at effect size because it can help you recognize whether the effect that you just tested, even if it's statistically significant, how much power it has, or how much impact it might really have in explaining differences. And oftentimes you'll find with large N, you have something that's highly significant, but the effect size is really small. And you say, well, there's still a lot out there that I'm not explaining when I have got that small effect size. All right, so that's it for Chapter 8. And next in Chapter 9, we're going to turn to linear regression.